All right. Hopefully nothing breaks. So last time we finished up magnetic fields. We talked about induction and transformers. And I went into a bunch of detail about some of the math behind it. And in particular, the idea that what's going on when you have Lenz's law happening, when you have induction in a coil, is something has to be pushing the current around that causes the induced field. And it can't be a magnetic force because we can come up with orientations where there's no magnetic force. And so it has to be an electric force. And the point I was trying to get to was that a changing magnetic field causes an electric field. And we leave the details out and just tell you to do Lenz's law and Faraday's law. All right, we tell you to do all the stuff with induction, but we don't tell you the cause of it. But the truth of it is that a changing magnetic field causes an electric field, and a changing electric field will cause a magnetic field, because a changing electric field will cause currents. And, you know, or a current will cause a changing electric field. So the mechanisms is that one field changing causes the other field. And that can be self-propagating. That can be something that continues on and on. If you think about, what example am I trying to think of here? Think about a coil, just a single coil by itself. You try to pass current through it, right? And so that current generates a magnetic field. The current you set, you turn a knob to say 5 amps, and you pass 5 amps of current through this coil. So suddenly a magnetic field starts. And and then of course there's a question: do you turn it on instantaneously or does it ramp up? That's all in the middle of stuff happening, which I do. The goal is to talk about what happens there. And when that field starts, you go from zero field to some field. There's a change in flux, and now we apply Lenz's law to that. What we find is that there's a current in the opposite direction. So that if we just have a coil by itself and we try to put current in ourselves, it resists it. It acts like a resistor. Because we'll get an induced flux change. Sorry, we'll get a flux change in it, and then we'll get an induced magnetic field to stop that flux change, which gives us the opposite current. And then similarly, when we have a current flowing through a coil, our 5 amps on the power supply, and then we cut it off, that causes a flux change. And the coil tries to maintain the same level of flux. It replaces the missing flux by continuing to flow current. That sounds kind of weird, right? But the gist of it is that coils act sort of like the analog to capacitors. Capacitors start out resisting the flow of current. Instead of they start out allowing the flow of current and then stop it by building up potential difference across the plates. So they store energy. You put some energy in by putting current in it. A coil does the same sort of thing, but instead of potential difference, it's current. Current is the thing that ends up being the store of energy in a coil. And the energy in both of these, in capacitors and in currents, are the electric and the magnetic fields. So we left some of that out, right? Talking about the inductance of a coil, how it can store energy. We left that out, but we told you about capacitors. Coils are the analog. But the point of this is there's a lot of things where we should tell you the electric field side of things, and then we tell you the magnetic field side. And if you look at it, they're mirror images. They're analogs of each other. One looks just like the other one in a sense, except you're changing something around, electric fields to magnetic fields, or potential difference to current flow, something of the sort. And these are all things that the modern world uses. Is your computers and your phone chargers and special would not work unless the behavior of coils is as I'm describing them now. And the same with the behavior of capacitors. So you're probably, the point of this is, today we're talking about light, and we're talking about it in terms of electric and magnetic fields interacting. And ultimately, in the back of your mind, you should have sort of a little bit of knowledge that you can store away that is ultimately electric fields and magnetic fields. They're all coming from the same place. They're all coming from charges, either charges moving or charges stationary. And ultimately, they're just different aspects of the same thing. Is that there's really one thing, and light being both electric and magnetic fields, it's ultimately kind of just one sort of field. But for reasons, it's going to be easier to talk about it in terms of both electric and magnetic fields. All right, so in the lab, in the light lab, y'all have talked about, at least in some measure, one way of producing light, which is using atomic transitions. The idea is, deep down, light is kind of funny. Here, for this, we're going to treat light as a wave, as a wavelength, and it has a frequency, and it has some energy associated with that, right? Waves carry energy. Well, in the lab, I explained the view that light is a particle. Ultimately, light comes from charged electrons changing their energy level inside of an atom, going from a high state to a ground state. And that was why you saw specific spectra lines, was because there were specific energies that were allowed, and those corresponded to specific frequencies. And of course, we can go back and say, oh, well, light is a wave. If we know the frequency, we know the wavelength. And so we discussed the wavelength about it. That works pretty good for things like visible light and stuff nearby it in frequency and wavelength. But you can more crudely generate light or generate electromagnetic waves just by moving some current around. So in this diagram, what we have is an alternating current source of some form. Like the very first radio transmitters were basically giant generators. And the model you can have in your generator is take a motor, run it in reverse, power the motor through the bit that turns, and then the coil turns inside of it and generates a current through Faraday's law. So we take some source, and what happens is initially this source has some current flow in some direction. All right, so it starts out, alternating current. It starts out at some instant, there's no current, and then it'll have some positive current. And what that does is it pushes charge along some wire. So what we do is we hook up a couple of wires. We don't make a circuit. That's the important thing. We don't make a circuit. We just hook up wires to it. And so because we're not hooking up a circuit, there's no complete path, but there is a shove of electrons down the wire, or a shove of a shove of current down the wire. And so it causes a potential difference on the ends of the wire, like a capacitor, one might think. And so that causes an electric field, which is shown in the diagram. And so over part of the wave that's going to happen, you'll have essentially a downwards electric field where you push the current upwards to cause the charge separation. Then over the second half of the wave, because this is alternating current, you have a downwards current and you have the opposite form. The downwards current causes positive and negative voltage on the opposite ends of the wire. And so it causes the opposite electric field. And so this is your electric field as a function of time. Now, the other thing to think about is, what does the magnetic field do? Because if anytime you have a current, it can generate a magnetic field. And so in this case, by the right-hand rule, your current comes out of the screen on the left of the current and into the screen on the right of the current in the first picture. And then the second picture goes the other way around. All right, so here is your magnetic field. So there is a magnetic field and an electric field created with this shoving around current with an alternating current source. All right. There's the image I want to show. The current that generates the electric field also generates a magnetic field, and it's sinusoidal. You can see the sine wave pattern in here. But what this does for the magnetic field is it puts the magnetic field at right angles to the electric field. Now, for various reasons, you don't need to think that it's going to look exactly like this, where the electric field, the magnetic field is zero at the same time. It doesn't have to be in phase. It does have to have the same frequency, but it can be out of phase. And it doesn't have to be the way it's drawn. It can be drawn, well, actually, probably the electric and magnetic fields are going to be roughly oriented that way. I don't know, you can have phase changes, it'll screw things up. We'll talk about that in a little bit. But in general, this is the image you should have of light as waves moving, coming from some source. And this is true whether it is the atomic transitions you saw in the lab with the, the spectra and the lights, or whether it's basically a radio transmitter, or kind of anything in between. All right, that's kind of the two ways to do it: is shove some charges around, or let atoms shove charges around. So it's a wave, it has some speed. This is the speed of the wave. And if you remember, with normal waves, the velocity is frequency times wavelength. Everything you learned in waves at the very beginning of the semester still applies here, except for a few small details. All right, is when we talk about waves like sound, we were talking about physical particles that were being moved about. All right, it was a longitudinal wave because there were collisions between air particles. Here, the medium is really kind of abstracted, right? Because it's a tangible thing in the sense that you can measure the electric and magnetic fields. It can have effect on things, but it's not something of substance. It doesn't have mass like air does. It has energy, but it doesn't have mass. And so some of the stuff, and a big example is Doppler effect. When we talked about Doppler effect in air, you had to measure all your velocities relative to the air. and I wasn't necessarily clear, but that was why you had a source speed and an observer speed, and you couldn't do things like set one of them at rest and have the other one move at the difference in the velocities. You had to consider the velocities relative to the air. And that's not, in principle, that's a thing that you have to do. If you fly an airplane, you have to consider your velocity relative to the air. Or if you pilot a boat, your velocity relative to the water. All right, so it's unusual in our normal circumstances. We don't have to pilot a car with our velocity relative to the ground. That's just the velocity. But in principle, the ground could be a treadmill. Imagine a very big treadmill. You can drive 70 miles an hour and only be moving 20 miles an hour relative to the ground if your treadmill runs 50 miles an hour the other direction. So, it's not in our normal thinking to do things like Doppler effect in air. We have to kind of practice it. Here, we don't have it. We don't have a medium that is a tangible, is a substantial thing we can deal with. It's just electric or magnetic fields. So things simplify out. Things get easier. I talked too much. I should have just kept going. Sorry about that. Radio waves can be transmitted. All right. So we've talked about ways of creating light, but light can also be absorbed. The energy can be taken out of the wave to do other stuff. All right. If I can speak, you can listen. The sound waves can be generated and absorbed. So can light. And so for radio waves, a receiver can just be a wire. In this case, the electric field comes along. And so first it experiences the electric field up, which means the positive charges will move along the electric field and pile up at the top of the wire. And so you will have a potential across the coil and across the capacitor. So the coil there is labeled L and the capacitor labeled C. It's what's called a resonance circuit. The idea is that it picks out a particular frequency of light so that you don't just listen to everything at once. Is some wavelengths of light incident on this receiver just won't, the energy won't be stored for later. It'll be kind of deconstructive interference. But for particular values of the frequency, which correspond to the values of the coil and the capacitor, it will resonate. It'll be constructive interference, and it'll pick out that signal. But the gist of it is the electric field will shove the charges around in the wire, and it shoves charges around in the coil and the capacitor, and you can use that. All right, here we show a transformer, which lets you pull out the information and do things like amplify it and put it on camera or put it on a television or put it in your speakers or whatever. And it works, right? The magnetic field should work the same way, right? Is that if a magnetic field at right angles, you have a set of wires. The magnetic field is changing. This wire feels a flux. It's not a coil, so that seems a little weird. And you're right, it is a little weird. What happens is it's very ineffective at picking up magnetic fields, but it could pick up some magnetic field stuff.
It's still got some area. Because it still has some area.
Yeah, it's not a complete coil. The coil is a very weird and unusual shape. You make a normal coil, this thing is ineffective with electric fields, but it's very effective with magnetic fields. And here you change the flux through this loop. That puts an EMF into the ends of the loop, which moves current through the coil and capacitor and picks it up the same way. All right. And in this, the electric field would be essentially parallel to the surface of the loop. So it would push charges around, but it would push charges around kind of on both sides of it, and you end up not getting what you expect out of it. Right? It's ineffective. So We described radio waves. Radio waves are this pushing and pulling currents. And then on the other end, visible light, ultraviolet, X-rays, gamma rays, those are all fairly much atomic transitions, the stuff you saw in the lab. And then there's some in-between stuff. Generally, any of these can be atomic transitions, though they can, or molecular transitions. The analogy is you have a big molecule that has lots of energy states, and some of them are fairly close together, so the changes can be low energy, which means long wavelength. So any of these can be transitions in energy state for atoms or molecules. But in general, the radio wave stuff that you deal with every day is pushing and pulling charges, and the atomic transitions are all higher frequency, shorter wavelength, light to gamma rays. I do say they're all possible because one way you can produce light is just to heat an object. Heat an object, it gets thermal energy. That thermal energy can be radiated away, usually through atomic transitions. Right? That seems to be the mechanism. Is you have a material, so you have lots of molecules, and light is produced through changes in the energy state. And the energy states are close enough together that it looks continuous to us. So the stuff that I talked about, we talked about heat this year, didn't we?
Yeah. Okay,
yeah. That stuff falls in, anything that you can produce from thermal energy falls in here as well. So all waves have frequency and wavelength, and you can write it as V as F lambda. But here, the speed of light is a constant. So you don't have to go looking for the velocity. And what's going on, this is kind of a thing, is, excuse me. When we talked about waves, we talked about the velocity of a wave in two ways. We said, if we know the frequency and wavelength, we can calculate the velocity, right? And that's just counting the number of oscillations you see and measuring how far apart they are, right? But the wave was on a medium. It's in air, or it's on a string, or it's through a material. And whatever the form of the wave is, we can deduce the velocity from material properties, right? For a string, it's tension divided by mass density. Or for air, it's the thermal energy, a function of the thermal energy in the air divided by the mass of the air particles. Right? It's this weird thing. I never made y'all go through that. But there's different ways of finding the velocity from the material properties. This is the material properties. This is both ways of doing it. What the speed of light is going to tell you is ultimately the material properties of empty space, of the vacuum, of the universe, in a sense. All right, and this is where that epsilon naught and mu naught that kept coming up in electricity and magnetism, that's where it comes from. Good enough. Going here. First, we do some examples. All right. The range of visible light, given some estimations for the frequency, you want to calculate the wavelength, is pretty much plug and chug. But what you get, if you do this, is numbers on the order of 10 to the minus 7 meters. All right, so we convert it to nanometers, which is 10 to the minus 9 meters. All right, so all of this stuff is 10 to the 9 nanometers per meter. And so what we get out of that is the range for visible light. When I quoted it to you in the lab, it was between 400 and 700. For these numbers, it's between 380 and 750. And of course, it varies. You know, it's how you know, in people's eyes, there's chemical receptors in the cells. They're going to react at certain wavelengths, but they're going to react to certain intensities, you know, with certain efficiencies as well. All right, so you know, some people may be able to see a little stretch these out further, or they may not be able to see certain wavelengths. When I worked in the lab, I worked with an infrared laser, and it was 800 nanometers, and I swear I could see it. Right. I mean, it projected on the wall. But you can also be fooled by that too. You know, we had detector cards that would fluoresce when you needed to see it. So, and then infrared stuff. When I worked with, ultraviolet, I worked with an ultraviolet laser, and it looks blue. And you want to be careful about lasers. Green lasers are what's going on. They take an infrared laser and they double the frequency through some interesting stuff. Basically, they add the laser beam to itself through a material that causes some indifference products, and so you get a double the original beam, and that turns out to be green. So be careful of green lasers. Well, any laser, you know, don't point lasers in your eyes, obviously, but if you had 3 of them on a table and someone held a gun to your head and said, point this at your eye, pick the red one. Well, of 3 of similar energy, right? The idea is compare the energy and the wavelength. There's a point to this. The point to this is when we get into atomic behavior, blue light is more energetic per particle. So for red and blue lasers to put out the same energy, red has to put out more particles.
Is that just because of what you were saying earlier, that the longer wavelength is lower energy?
Yeah. So this is the thing is we quote the speed of light, 3 times 10 to the 8 meters per second. And that is an approximation. There's actually a whole story about the finding of the speed of light, because you go back 600 years in history, people were not aware that light had a speed. They thought that information transmitted instantaneously between source and observer, because you really could not get far enough. Like the farthest away people could see a signal by light was about 40 or 50 miles. And the first measurements of the speed of light were 2 people 30 miles apart on hilltops. One of them would light a lantern and shine it. And then when the light got to the other end, that other person would flash their lantern. And what it was doing was measuring the reaction times of humans. The light was so fast that all they could get was the reaction times of nerves in the body. So it didn't work, but people realized that maybe there is a speed there. And so the first measurement was with the discovery of the Galilean moons around Jupiter. People realized that this was a possible clock because the orbits were very regular. If you could see eclipses of the moon behind the planet, they would occur at regular times, and you could use it as a clock. So maybe you could do things like sailing. You know, you could sail your vessels across oceans, where if you had a view of the sky, you could use Jupiter to find the time and then use that to reckon where you were. This is you can go look this up online. The problem with the determination of longitude. Finding latitude is easy, you can use the stars. Finding longitude is hard because that's measured from a particular spot in the middle of England.
They just fixed it by inventing clocks.
By inventing better clocks. Yeah, they had clocks.
Worked on them. Shit.
They needed a clock that worked on a ship, and that's what they did.
We talked about that at length in like British Empire.
Yeah. So the first attempt was to try to time the eclipses of Io behind Jupiter, and it failed because the eclipses were routinely about 10 minutes early or 10 minutes late. And they noticed a pattern in it which corresponded roughly to the orbit of the Earth. Basically, they had a model said, they had the heliocentric model beginning, and they come to the conclusion, I've got plenty of time, they come to the conclusion that the delay showed up because sometimes they were measuring the eclipses when Earth and Jupiter were as close together as they could be. And then 6 months later, they were roughly as far apart as they could be and still make the observation. So, 5 or 6 months apart.
So the eclipse wasn't late or early, just us seeing it.
Right. The information of us seeing it was delayed by the time it took light to cross the Earth's orbit, which they got a reasonably good number. They got 10 minutes for that value, which the value today is 8 1/3. Well, yeah. So it let them do things like measure to, they also, that's a problem. They also had an error in the size of the Earth's orbit. So they got a speed of light at about 200,000 meters per second, or 200 million meters per second, translated out of, 15th century Italian units or whatever it was. 16th century, sorry. No, sorry, contemporary Galileo, probably 17th century.
If it was Newton, it would have been 17th century.
Yeah, that's roughly in that area. So in the past, last Thursday, they figured it out. So 200 million meters per second out of some units. That was key though, because it told them, hey, there's a speed, we can measure it. And so they kept measuring it. And there was multiple different attempts. There's this thing, which is a rotating mirror. The beam of light from a source will hit your eye only when the mirror is in the correct orientation. So if you know the rotation speed of the mirror, you can tune out, you can figure out how far the mirror rotates as the light is going between the rotating mirror and a fixed mirror very far away. So 70-kilometer round trip will correspond with some rotation speed that doesn't show you flicker in the light. The idea is that the mirror rotates enough to where you have the correct angle of incidence. And so that improved it. And then they had things like a toothed wheel, is that if you had light pass through a toothed gear and come back the same path, it wouldn't flicker if the light could go through the teeth and then come back and go through the next tooth, which meant the toothed wheel was rotating appropriately. And then they had what's called interferometry attempts to measure it. And they got very, very, and then they had other things like put radio waves in a cavity and figure out the resonant frequency of the cavity and work backwards. And so they got to this number and it was like, we're tired of trying to figure it out. That's the definition. That is the speed of light. And what they did is change the definition of the meter and the second to correspond. Because they didn't like those. The second was 1/31 millionth of the year 1900, from noon January 1st to noon January 1st next year. Which is weird. That's a horrible definition because you can't reproduce it. You can't not relive 1900.
Yeah.
And then the meter was 1/40 millionth the polar circumference of the Earth going through the prime meridian. Or it might have been through Paris, I can't remember. But either way, it's a horrible definition because the Earth is not uniform. It's not spherical, it's squashed, and then it's not even uniform that way. It has bulges and it has mountains and surface features. So it's a horrible definition, and no one can measure it. So, that's why they had all these bars of metal with notches in them, and they had the prototype kilogram. And that's why the English had the prototype yard and inch. It's better than trying to use their ideas. But what we're doing now is making science experiments that you can build. So you define the second, and it's counting atomic transitions in an atomic clock, basically. And then you define C, you define the meter. And then you define some of your other stuff. Defining the kilogram now is using Lenz's law and Faraday's law, and basically using torque, using the, making a balance. And one end is your kilogram, and the other end is a particular coil passing current through it and attracting other stuff. I think it has to be another coil so you can calculate it. You can't just like put a bar of iron in it. So it's particular, but you can look up that. It's called a watt balance. Anyway, defining the speed of light was a weird thing. But there was a prediction for the speed of light. When I showed you all that stuff last Thursday about the math, talking about the divergence of the electric and magnetic fields and the curl of the electric and magnetic fields, those were what were called Maxwell's equations. Maxwell was a guy who was studying electricity and light and magnetism, and he jumped to the conclusion, appropriately, that light is electric and magnetic fields, and that electric and magnetic fields are aspects of the same thing. And so he made a prediction using the constants that were available to him to define the speed of light and to define these constants effectively. And so if you take epsilon naught and mu naught, you take the values we have, you multiply them together, you take square root, you take the inverse, you get the speed of light. And that's not an accident. So the speed of light, I told you about calculating the material properties of the universe. That's that. Epsilon naught and mu naught. If you remember, epsilon showed up in capacitors. And it was effectively, we stated it as K, the dielectric constant. But it comes in as a function of epsilon, which is the permittivity of the material. So epsilon naught is the permittivity of vacuum. And then talking about magnets, you can talk about a material, it has what's called a permeability. How easy is it for magnetic field lines to get into it? So mu naught is the permeability of space. So this is using the material properties of the universe to calculate the speed of waves in it. So there's some other stuff in here about light. Light has a speed. So if you see something, you're really seeing the events that occur earlier. Like if I take and drop this eraser on the table. Drop one, it makes a noise. All right, so the events happen, and then the light travels across the room to your eyes, and you see it. And so on the normal scale, that's tiny. We're talking something like 1 nanosecond per foot. So between us with this social distancing, it's about 6 nanoseconds old. And if you're watching on the Zoom call, then, if you're watching live, it's going to travel to your home, which is 30 miles away, or on campus. It's going to be on the order of microseconds, not counting all the processing that happens inside of it. So our experience is if something happens, we see it instantly. But something like a supernova and a star blows up. By the way, there's 2 forms of that. You should take the astronomy class to find out about it. It's interesting. One is a big ball of carbon blows up and nothing's left. The other is a big heavy ball of iron blows up and a bunch of stuff is left. And that is not what I teach my high school kids. You see events in space they're light years away. The term light year is obviously a measure of distance, but it's not obvious what it is, but it's exactly what it sounds like. It's the time light takes to travel in a year. You can calculate it out. It's 10 to the 16 meters, I believe, or kilometers. Doesn't matter. It's a big number on the exponent. It's far away. And then these things are hundreds of light years away. So or actually, most supernovas we know of now are thousands to millions of light years away because they're easier to see in other galaxies. They don't happen that frequently. So you look at lots of galaxies to find them. So they are sources of light produced long in the past. And of course, in astronomy, all right, if you notice this picture, it's got a lot of red in it. All right, the light is affected by the medium it passes through, and space is not completely empty. It's got stuff like dust and reasonably more high-density gaseous clouds than empty space. Empty space has like 1 particle per cubic centimeter, and then you'll have clouds that have like up to hundreds or thousands of particles. But the point of it is there's material that hasn't formed up like planets and stars and big nebular clouds, and it still absorbs light. And it tends to absorb blue light or scatter blue light. And so the red light tends to get to us better. And that's why images from space tend to have, well, other than the fact that they're all color corrected. But red wavelengths get through a little easier, and infrared wavelengths get through a little easier. Longer wavelength means they're a little harder to absorb and a little harder to scatter. Light waves carry energy like any other wave. If it didn't, your microwave wouldn't cook your food. Which, by the way, if you can measure the speed of light in a microwave, you need one of these big novelty-sized chocolate candy bars. Put it in there, take the turntable out. And what happens is, in a microwave, you have a bunch of reflectors of light. You're going to get standing waves, which we talked about in waves. And so you can measure the nodes by where the candy bar is melted. And that gives you a distance, and you can get the frequency off the microwave, and use that to calculate frequency and wavelength, gives you the speed of light.
So would the nodes be where it is melted or where it is?
Well, nodes would be where it isn't melted.
Okay, that's what I was saying.
But you would use the antinodes. They'd be half the wavelength apart, so the melted spots. And for a microwave, microwave's about 2 to 3 gigahertz. So you're talking about 1 centimeter. So it's easily measurable. You just have to make sure to do it before the whole thing melts. So without proof, we talk about the total energy carried in the wave. I say without proof, it can be proved, honestly, but we skip some details, right? Because if you remember capacitors, the total energy in a capacitor was at some point a function of the potential across its square. And what was going on is you start with a capacitor that's empty and you charge it up. And so for every electron you shove onto one plate and take off of the other one, you create a small bit of electric field, which means you make the next bit of charge you put on it harder to do. You do work against the stuff you previously put on it. And so you ended up with some average. And we expressed it in terms of the potential, but you can express it in terms of the electric field, because the electric field and the potential are related. And so the energy in a capacitor looks like the electric field squared. Similarly, in a coil, we didn't discuss this. The energy in a coil, the energy stored, right? The stuff that is involved in Faraday's law and Lenz's law. You know, you trying to move the currents around, that energy gets stored is a function of the current in it. And a function of the current is really a function of the magnetic field, since the magnetic field creates the current, and the current can create the magnetic field. So ultimately, there's energy in the electric and magnetic fields, and the energy goes as the field squared. But what we talk about is the energy density, because it's kind of hard to talk about the energy of a wave, because the wave just goes on until it gets absorbed somewhere. And who knows for how long it propagates. So we don't talk about the total energy, we talk about the energy that fits in a particular space.
Wouldn't it be better to use like energy per unit length of the wave? Because I don't think the wave is having quality.
Right. It's the way to think of it is, say you have like a box and a hole in it. The hole has some area, and then you have a light inside. The light can come out, so it's multiple rays of light as waves. So it looks like an extended, a thing that does take up space. Right? And so we're thinking of light going through an area some distance. Right? So you're right, it would be energy along a distance, except we want to capture, is it in all directions for some distance, or is it through a hole, or is it incident on a thing? The goal is to get to intensity, right, which is power that hits a surface. So power divided by area of the surface. All right, so now, for various reasons, we want to talk about the average, not an instantaneous energy. All right, because the waves vary. And so if I plot the wave here, no, don't do that. So I'm going to plot the electric field here. If I take the average of that, it's 0, right? Because there's just as much up as there is down. But the average energy can't be 0. But since the energy depends on the electric field squared, let's plot instead in blue the electric field squared. That'll always be positive. And then you can take the average, will be something like that. We take the RMS, we talked about that, I think, a little bit when we talked about speeds of particles. But it's this procedure of just calculating, you square the electric field, take the average of it, and then you take a square root to get the electric field average. So a lot of times you don't have to worry too much about this, because we're always going to state the average energy. We're not going to state the peak energy, or we're going to state the average field, not the peak field. So you're always going to be working usually with the average energy. And so it looks like this function. And then we can go one more step. If we're in vacuum, this relation will hold. I give that without any proof. But you've seen this sort of relationship in the units before. This is the velocity the velocity selector equation. When you have electric and magnetic fields and they're crossed, there'll be one velocity particle that has no deflection, no force on it. Right? And so the units for magnetic field look very much like the units for electric field divided by speed. And so that's what we have here. Now, what that means is, instead of, in the previous slide, going back a slide, instead of adding the contribution from the electric fields and the contribution from the magnetic fields, we can just work with one or the other, which makes it easier. We don't have to measure both, we just measure one of them. And since they're equal, right, is they effectively, one of them contributes half and the other contributes half the energy. Now, of course, we say that in vacuum because if the light goes through something like glass, then all bets are off. The light's interacting with matter, and you don't know what happens. You have to measure it. So in general, you're always going to see things like the energy per unit volume is a function of the electric field squared. All right, so example problem. We have a wave that has an electric field with a maximum value of 800 newtons per coulomb. And we want to find the average energy density and the maximum value of the magnetic field. All right, so that's not too terrible. All right, first, that lets you get the RMS value. So that's 800 divided by 1.4. I got a text message. Oh, nice. I got to use the calculator. Is all right. So now the energy squared, sorry, the energy causes the electric field squared. So Coulomb squared per Newton meter squared. So if we look at that, we will have a Newton on top. We'll have the Coulomb squared cancel out completely. We will have a meter squared, and then we'll have a number. I want to say that notice it's a unit of pressure. That is weird, right? That is also a little bit of foreshadowing. But you can convert this unit from, multiply meters top and bottom. This is joules per meter cubed, and that is energy per volume. So that works okay. And then we want to calculate the magnetic field. We're going to use E is CB. So B is 800 newtons per coulomb divided by 3 times 10 to the 8 meters per second. And it'll be something in Tesla. .67 times 10 to the minus 6. And that kind of makes some sense. That's not too terrible. So a lot of this is, notice the type of problem it is. One equation, plug and chug. Not too terrible of a deal. It's identifying the type of problem it is. All right. So all right, what you was talking about, the energy over a distance instead of energy per volume, right? So that makes sense if it's one light ray coming through, a wave that takes up no space. But generally you have like light coming through a window, it comes through all parts of the window. And so what we want to calculate is an intensity, which is the rate at which energy comes through an area, or is incident on an area. So that's what we have here. S here is what we call the intensity, and it's the power divided by the area. But the power is the total energy divided by the volume. The power is the total energy divided by time. And then the total energy is the volume. And here the volume is the area of this surface times the distance the light covers, which is the speed times the time. So all right, so this is X. And so the area drops out of it, and so does the time. The intensity of light looks like the energy per unit volume times the speed of light. That kind of makes, from a unit point of view, it makes sense. We may be getting to the point where it's time to let it go. Yeah, we're getting there. But what this does, it explains how solar panels work. Right? So what's going on in a solar panel is you have some receiver and light coming in. And then in the receiver, you generally, for a solar panel, have a crystal of silicon with some stuff doped into it. And it does the atomic transitions in reverse. It takes in the light, puts the electrons in higher energy states, or in lower, or it essentially ionizes, a particular atom, which then allows that electron to flow, and it goes through a circuit and comes back, or it's pushed out, and it comes back and recombines. So it generates a potential difference across the material by light hitting on it. So for it to be effective, you have to get enough light. And so the idea is we have some light that has an electric field value. So the idea is to calculate the intensity of the light hitting, right? And so that's pretty straightforward. We would do from our derivation before. So S is U times C, but U here is the energy per unit volume, and that is epsilon naught times the electric field squared times C. And of course, this is at the top of the atmosphere, so it's in vacuum. If we did it at the bottom of the atmosphere, you'd have to calculate a magnetic field because it passed through air. Generally, you wouldn't bother. You could approximate it, but this is calculatable. Coulomb squared per Newton meter squared. 750 newtons per coulomb squared, 3 times 10 to the 8 meters per second. So units on this, you'll have newtons. The coulomb squared will cancel out. You'll have meters on the bottom, and then you'll have seconds on the bottom. And then you really want to get to something that makes more sense, right? Because the units on this is power versus area should be watts per meter squared. So meters on top, meters on the bottom. And then this is joules per second per meter squared, which is watts per meter squared. And you calculate this out. Yep. 750 squared times 3 times 10 to the 8 times. What we get is approximately 1,500 watts per meter squared. And then, so for solar panels, what happens is the light passes through the atmosphere, you lose about 200 watts. It's about, actually 100. It's about 1,400 watts at the surface of the ground. And then you have to capture it over the entire area, which means you have to steer the solar panel around to point at the sun. because if it's off at an angle, you have the effective area, so there's a cosine theta, like in Gauss's law and finding the magnetic flux. And then you have clouds come over, so you only get a fraction of the light. So the effective intensity of light over a day is like 200 watts per square meter. Because, you lose half because it's night, and then you lose for cloud cover, and then you're averaging over a long period of time. And then your solar cell is like 10% efficient. So you have 1,500 watts of intensity, which is the power coming from the sun. Right? And the power from the sun is on the order of 10 to the 26 watts. But the Earth's orbit's big, so you get a little fraction of that, and then you cut it down to about 20 watts per meter squared at the power point, at the where you measure the potential difference across it. You can draw about 20 watts out of a square meter solar panel. In principle, there have been improvements on efficiency, and you can get a beautiful sunny day like today and get a lot of energy, or you can get a cloudy day and get not much. So we're going to stop there, and next time we're going to do Doppler effect. But I want to point out a few other things before I let y'all go. Light has energy. That's great. We talked about where that is. Other things that have energy, right? We talk about kinetic energy. That's something that has speed. It has momentum. Right? Things that have speed have momentum. Light has a speed. It doesn't seem like it should have momentum, right? Because it seems like it doesn't have mass. It doesn't have mass. But if you think about a wave, like in a medium like air, right? The wave itself abstracted is going to carry energy from one place to another. And then if it's absorbed by a material, it can cause it to move. Like imagine you have a free end of a string. The wave moves at the end. It can move, it can move all those cups that were hit in the lab. So in a sense, the wave can impart momentum to other objects. Now the difference between those waves and light is the mass. Is that light doesn't appear to have a mass, and that doesn't make a lot of sense. So two things that come out of it is we can measure the momentum imparted by light, right? Because you can do things like put solar cells out in space and they capture the light from the sun and are accelerated. They get a change of momentum. And the other thing is it gives you kind of a hint that there's something missing out of our description of light, which is where relativity comes in. Right? If you remember E equals mc squared, that is relating energy and mass. They are effectively the same thing. So anything that has energy will have momentum as well. And you can calculate it out. It ends up being the momentum is the energy divided by the speed of light for light, and then it's complex for actual objects. So that's extra stuff. This week, a lot of this week is extra stuff. You'll have a homework on it. There'll probably be a question, but a lot of the details is stuff that is interesting, but not worth testing on, if that makes sense. So I get to spend a lot of time telling you about it, not so much doing it. Do y'all have any questions about anything? Were y'all entertained? I hope. All right. Have a good day. See you Thursday. Oh yeah, Thursday's the exam. So no class that day. Exam's in Center for Science M70. 7 o'clock.
There's one thing I wanted to ask about.
Sure.